So VC dimension and L dimension has some difference. This is theorem for any class hypothesis class H. VC dimension is less than or equal to L dimension, and there are classes for which strict inequality holds. Furthermore, the gap can be arbitrarily large. This is because L dimension has more freedom. So for instance, in the previous page, essentially for the shelter tree definition, so there are entire hypothesis class and there are sub-hypothesis set that has zero response for the instance v1 and one output, the output label 1, a subset of hypothesis. They are disjoint and the union of these two hypothesis set is the original total hypothesis set H. Okay. And for the second level, with instance v2, we make a two subset of hypothesis, which make a zero output for the v2 instance and one output for the v2 instance. But for here, we don't care whether this subset that has the output 1 for the first instance v1, we don't care this subset of hypothesis has both response 0 and 1. It is totally okay. This subset of hypothesis, all hypotheses belong to this subset of hypothesis class having output 0 for instance v2. It is absolutely fine. But for VC dimension, when we have two instances v1 and v2, we have to be VC dimension 2, we have to have some hypothesis having response 0 and 0, having response 0 and 1, having response 1 0 and 1 1. We have to have some hypothesis having this response, having this response, having this response, having this response. Okay? In other words, when we have VC dimension 2, which means the hypothesis class can shatter 3 v1, v2, v2. Okay? If the VC dimension is 2, then the hypothesis class can shatter the 3 having instance v1 at the first level and v2 at the second level. Okay? Because VC dimension by definition can make any combinations, any possible outcomes for the two instance v1, v2. But for L dimension, we can replace v2 for this side using another instance v3. Essentially, we can introduce another instance v3 for only for this subset of hypotheses. Okay? This subset does not care whether this subset has both response 0 and 1, but we just care there exists a new instance v3 that can make both response for this subset of hypotheses. That is key difference. Therefore, by definition, L dimension always bigger than VC dimension. Because VC dimension, the shattering example, is one special case of shelter tree for the L dimension. So for the L dimension, we can define more deeper shelter tree using different instances for the same level. VC dimension, for the same level, we have to use the same instance. But for the L dimension, we can use different instances for the same level. Okay. So this is another very nice example that can explain why VC dimension and L dimension has such difference. Consider very simple hypothesis class, boundary hypothesis or interval hypothesis. That input domain is from 0 to 1 finite interval unit length. And let's consider hypothesis class having unitary boundaries. So we have output value 1 when input x is strictly less than a. Otherwise, the output is 0. So we have 0 to 1 is input interval. And when we have a, this area having value 1 and all this area having value 0. This is one hypothesis, and which will be labeled by A. Okay. Then this hypothesis class has VC dimension of 1. Why? When we have this single instance, we can make the output of this single instance to be 1 using A strictly bigger than this point, so that this, then the output of this single instance is 1. We can make this output to be 0 by using A less than this. Okay, so we can make both 0 and 1 for this, for any single given instance. But for any two instance, we can make 1 0, and we can make 0 0, and we can make 1 1, but we cannot make 0 1. This is not possible. So this is this has VC dimension 1. Okay, but for the L dimension, we can make such tree. For the first level, first root node, you can set the 1 over 2. So there are some subclass of this hypothesis class, a subset of this hypothesis set that has 0 response and that has 1 response. And when we have this 1 over 4 and 3 over 4, again there are subset of hypotheses having value 0 0, having value 0 1, and so on. So basically we can simply go deeper this tree using some pivot point. We can easily find such pivot point. So we can easily show that L dimension of this very, very simple hypothesis class, of which dimension is 1, but the L dimension is infinite. Okay? So this example is very nice example that can explain. In some cases, L dimension is much bigger than VC dimension. So using L dimension, we can design a simple algorithm for infinitely many hypothesis case. It's called standard optimal algorithm. So as before, we first start with the entire hypothesis class V1, and at each time we receive a new instance xt, and then make a prediction pt, and then get the true label yt, and then update the vt plus 1. The standard optimal algorithm is like the majority vote. So we first find subset of vt that has output label 0 for the new instance xt, and output value 1 for the new instance xt. So we have vt1 and vt2. And in the previous case, for the finite hypothesis case, we just simply check the cardinality of vt1 and cardinality of vt2 and follow the majority. If the vt2 cardinality is high, okay, so this is 0 and 1. If vt1 cardinality is high, rather than vt0 cardinality, then we choose 1 as the output. But the problem here is, since the hypothesis class H is uncountably many, it is possible, so we cannot counting how many hypotheses in vt0 and how many hypotheses in vt1. So instead of the number of hypotheses, we measure the size of its subset vt0 and vt1 using L dimension. Okay, so if L dimension of vt1 is larger than the L dimension of vt0, then we set 1 as the output prediction. So pt is simply argmax of L dimension. If both vt1, vt0 have the same L dimension, then it is okay, just randomly choose one of label. And then receive the true label. And one nice thing of this is, if the current prediction is long, so the yt is not equal to pt, then the other side, the remaining part of our hypothesis set will be smaller than the current hypothesis. So, which means, so when we compute LDIM VT, whenever there is some mistake by this simple argmax rule, then L dimension of VT strictly larger than L dimension of VT plus 1, because we choose subset that has the largest L dimension. Okay, so the L dimension of VT is monotonically decreasing, and also whenever there is mistake, L dimension will strictly decreases. So which means the maximum possible number of mistake for this standard optimal algorithm rule is L dimension of V1. Okay, L dimension of entire hypothesis class A.